Daihui Liu from Purdue University and from mechanical engineering. She's gonna talk about physical informed neural networks for shear-induced particle migration. Yeah, Daihui, we can start now.
Okay, thanks, Professor Lin, for your introduction. Hello, everyone. My name is Daihui Liu. I'm studying mechanical engineering at Purdue University. Professor Evan Christoph is my PhD advisor. I'm very excited today to present to you my recent research on physics-informed neural networks for shear-induced particle migration. Let's get started. The problem we're trying to solve is particle migration in positive flow, as shown in the left diagram. The continuity equation has been discovered by Phillips et al. This equation essentially is a balance among collisional flux, viscosity change, and Brownian diffusion. In the equation, Kc and K-eta here are empirical parameters of collisional flux and viscosity change. And Packlin number here is defined by the ratio between shear diffusion and thermal diffusion. Phi is the particle concentration, and eta is the viscosity of the suspension, which is defined by this empirical equation, and C is another empirical parameter. Below here is the momentum equation, and G star is the dimensional pressure gradient. On the left part, here are some typical scales of the parameters. This phenomenological model has been widely used in modeling of shear-induced particle migration in the low Reynolds number flows of suspensions. Well, however, the model's parameters were only calibrated against experiments in an annular quiet flow. While in positive flows, the model is only in qualitative agreement with the experiment. So in this project, we're trying to calibrate the parameters using machine learning, or more specifically, physics-informed neural networks, aka PINs. Here's the architecture of the PINs. The input here is y coordinate. And then we have two neural networks, one for velocity and the other for particle concentration. The outputs are, in the outputs, we have velocity and the particle concentration, and the subscription B here means the constraints from boundary conditions. Then we can form, then we use the velocity and particle concentration to form the momentum equation and continuity equation. Remember that the unknown parameters we mentioned before are included in those two equations. With that, we can form the total loss function. And by minimizing the loss function, we will be able to get the optimal weights in the neural networks, as well as the previously unknown parameters, Kc or K-eta or C. The code for this project is based on the implementation by Razi, Perdikaris, and Karniadakis in their paper in 2019. In the loss function, we have three parts. The first part is the errors between the predicted value and the training data. The second part is physics constraints. Here, MSES comes from the continuity equation, and MSEM comes from the momentum equation. The last part is boundary conditions, which depends on specific cases. And in the loss function, we have weights, W, U, W phi, etc. And the weights may not be uniform, so we can adjust the values to adjust the weight of each loss term. Before we get into the positive flow, let's first verify the Payne's approach in an annular quiet flow. The loss function here follows the same form as I introduced in the previous slide, except that there's no boundary condition constraint on a velocity because the no-slip boundary condition has been included in the momentum equation here. And the continuity equation is reduced from the one in the previous slide. We choose this model because this model has been previously calibrated by a classical approach. And our goal here is to find the ratio between Kc and K eta using Payne's and then compare the value to experimental results. Here are the comparison when the bulk concentration is 0.55. The left panel is the velocity distribution against radius, and the right panel is the particle concentration. The blue dots represent experimental data from Phillips et al., and red curves are Payne predictions. On the right panel, the black dashed curve is theoretical solution by solving the ODE. Now, it turns out that Payne predictions agree very well with experiments, and the ratio predicted by Payne is very close to the experimental observation by Phillips et al. Now we've verified the approach, we can use it to learn unknown physics in positive flow. Let's first take a look at the non-Brownian dense suspension, which means we assume the Peckley number is infinity, so we can simply drop the Brownian term, the Brownian diffusion term in the continuity equation here. And the other two terms are the same as we discussed before. Here is a representative result when the bulk concentration is 0.1. As you can see, Payne works here, and Payne prediction is much better than theory. More importantly, Payne found that the ratio between Kc and K eta equals 0.1, while Cole et al. Used 0.66. This number, 0.66, comes from the experiment on an annular quiet flow, and it is not very accurate in positive flow. Therefore, Payne provides some new knowledge in positive flow of suspensions. Having shown that Payne provides good results in non-Brownian case, now let's move to the Brownian case. Now in this continuity equation, we have added the Brownian term here. And then the momentum equation can be further reduced to this form because the experiment results have shown that the velocity can be approximated by a parabolic profile. In the Brownian suspensions, because of the extra unknown parameter C here in the viscosity, experiments haven't been properly analyzed by this model. Now with Payne, we could do it better. Here is a representative result of Brownian suspension. We compare the Payne results to the experiment from Frank et al. When the bulk concentration is 0.34 at different Peckley numbers. As you can see, Payne results agree very well with experiments. And again, the agreement is better than theory. More importantly, using Payne for the first time, we get to know the parameters K, C, K eta, and C for Brownian suspensions. Here is a summary of parameters solved by Payne under different Bach concentration and Peckley number. You can see that this the values of the parameters vary with a different Peckley number and phi. To summarize this talk, we have verified the Payne approach for solving the inverse problem of radial particle migration in quiet flow. And then we identified the unknown or empirical parameters in the physics model through Payne. And Payne results show that the empirical parameters vary with Peckley number and Bach concentration. Another point I'd like to share is that Payne provides a new approach of thinking. The old way to use the phenomenological model from Phillips is to solve ODE directly. But to solve the ODE, we need to know the parameters first. While on the other hand, Payne doesn't require the parameters to be known. And the relative importance of different particle migration fluxes like collisional or viscosity gradient or Brownian effect, this flux, the relative importance of this flux can be uncovered via Payne. So I think that the model provides more useful results when it is incorporated with Payne than being used as a basic law to predict a particle distribution. Well, thanks for your attention. I'd be glad to answer your questions.
Yeah, we have some minutes. Yeah, we have 80 minutes, right? So anyone has some questions? So yeah, let me ask a question that way. So your pin is solving a PDE, right? ODE in your pin.
Yeah.
It's a PDE, right?
It's
ODE. It's ODE, right? It's ODE, right?
Yeah.
I see. Okay. And okay. So okay. So you said you have boundary condition, right? But so basically you have two sides boundary. So you solving a circle, right? So you have you don't have initial condition, right? Because you are just ODE, right? So you just have the one side boundary, right? At y equal to 0.
Yeah.
I
From
see.
y equal to 0 to 1.
I see. Okay. And all the weights you are tuned of all the weights. Okay.
Yeah.
Oh, okay. So you have two neural network, right? So that is that U and the UB are related or correlated? Is that or they are quite independent for the U?
I think physics, they are related because this UB is like we have like the velocity at some specific points at the boundary, and here U is the vector from y equals 0 to 1. But in the networks, they share the same weights of the network. Other than that, in the network, I don't think they are very much related.
Okay.
But it can be explained in physics.
Okay. So your MSES is what? Is the conservative mass, right?
Yes.
M means momentum, right?
Right.
I see. And so the U, MSU contains both U and the UB or just U itself?
Just the U itself, and UB is expressed in the last term, by the last term, MSE BC. That means boundary conditions.
The same for the phi B also goes into the boundary condition. I see. Okay, I see. So UB is also a function Y, right? Everywhere, right? Okay. Is that? It's the UB is a function y, right? UB is a UB is a boundary condition.
Yeah,
Okay.
yeah, only at boundaries.
That means the y is fixed. So I just want to understand what's UB. Is UB a function y or not?
Well, in physics, it is not, but I think in the neural networks, it is like it has some. It is related to y by the weights.
Yeah, because your input is y, right?
Yeah, right.
Okay. So okay. Here you basically represent UB as a function of y,
Yeah.
right? Okay. But also in reality, it's one unknown number, right?
Mm-hmm.
I see. Okay. Okay.